Okay, good morning again, everyone. Today we'll go on to 11.4. We continue on with probability. Today, our objective, we want to find the probability of mutually exclusive events. Okay, we'll figure out what mutually exclusive means, and then we want to find the probability of inclusive events. Okay. So what is mutually exclusive? Mutually exclusive events are events that cannot both occur in the same trial of an experiment. So for example, let's say here I have 30 students in a classroom and I have 14 females and I have 16 males, and I randomly select a student. Okay, what's the probability of me selecting a female? Well, that would be 14 out of 30. But I cannot select if I select one student, I can't select both a female and a male at the same time. That would be impossible. I'd select either one or the other. So we would say that the event selecting a student who is either male or female, well, those would be mutually exclusive events. You can't both select a female and a male. So mutually exclusive events are events that cannot both occur in the same trial of an experiment. Rolling a 1, like for example, event A, and rolling a 2, event B. So we have a number cube and we're going to roll it once. Okay, so you can't roll both a 1 and a 2 on one roll of a number cube. So they're mutually exclusive. Notice there's no overlap in this Venn diagram. Mutually exclusive. Okay. So how do we find the probability of mutually exclusive events? Okay, the probability of two mutually exclusive events A and B occurring is the sum of their individual probabilities. So for two mutually exclusive events, A and B, we say the probability of A or B, and this union symbol there, that means or, probability of A or B happening is equal to the probability of A plus the probability of B. Okay, so again, the union symbol means or. So when a cube is rolled, then what's the probability that is less than 3? That is less than 3. So you can add up the probabilities. You can't roll a 1 and a 2 at the same time. You either roll a 1 or a 2. So the probability you roll a number less than 3 is equal to the probability you roll a 1 plus the probability you roll a 2, or 1/6 plus 1/6 is 2/6, which is 1/3. Mutually exclusive events. Okay, so you probably would not have looked at that in terms of mutually exclusive events. You would just say less than 3, well, 1 or 2, so that would be 2 out of 6, or 1/3. Many ways to look at probability. Okay, so here we have a group of students that's donating blood during a blood drive. A student has a 9/20th probability of having type O blood and a 2/5 probability of having type A blood. You can't have both type O and type A blood. It's mutually exclusive events. Explain why the events type O and type A blood are mutually exclusive. A person can only have one blood type. So let's say a group of students is donating blood during a blood drive. A student has a 9/20th probability of having type O blood and a 2/5 probability of having type A blood. Then what's the probability that a student has type O or type A blood? Type O or type A blood. Again, so that will be the probability that they have type O plus the probability that they have type A. They're mutually exclusive events. So 9/20th plus 2/5. Okay, when you add your fractions, common denominator, you get 17 out of 20. Type O or type A. And think about this. What would be the probability of type O and A and type A? Think about that. What would that be? What probability would that be that you have type O and type A? Hope you figured it out. Wasn't very hard. Nada. It can't happen. You can't have both type O and type A. Zero probability of that. Okay, so let's continue on. Each student casts 1 vote for senior class president. Of the students, 25 voted for Hunt, 20% for Klein, 55% for Villa. A student from the senior class is randomly selected. Explain why the events voted for Hunt, or voted for Klein, and voted for Villa are mutually exclusive. Well, each student can only vote once. So, each student casts 1 vote for senior class president. Of the students, 25% voted for Hunt, 20% for Klein, and 55% for Villa. A student from the senior class is selected at random. What's the probability that a student voted for Klein or Villa? Okay, so again, they're mutually exclusive. So you add up the probability for voting for Klein plus the probability for voting for Villa, and you get 75% chance. Okay, so mutually exclusive events, they can't happen at the same time. Inclusive events, okay, are events that have 1 or more outcomes in common. When you roll a number cube, the outcomes rolling an even number and rolling a prime number are not mutually exclusive events. Okay, so you can roll an even number, 2, 4, 6, or a prime number, 1 is not prime, 2, 3, 5. But notice, okay, you do have something in common. So this was even number, and then prime number, what do you have in common is the 2. Okay, so inclusive events. The number 2 is both prime and even, so the events are inclusive. And in terms of the Venn diagram, you have 6 even numbers. Well, no, not 6 even numbers. You have the even numbers 6, 4, and 2. And then for prime numbers, you have the numbers 2, 3, and 5. But you can see from the Venn diagram that 2 is both common to even numbers and prime numbers. Oh, they just say it. So there are 3 ways to roll an even number, 2, 4, and 6. And there are 3 ways to roll a prime number, 2, 3, 5. The outcome 2 is counted twice when outcomes are added, 3 plus 3. The actual number of ways to roll an even number or a prime, though, is 3 plus 3 minus 1 equals 5. And why do we subtract 1? Well, because we're counting 2 twice. So the concept of subtracting the outcomes that are counted twice leads to the following probability formula. And this is for inclusive events. The probability of 2 inclusive events, A or B, occurring is the sum of their individual probabilities minus the probability of both occurring. Okay? So for 2 inclusive events, we say the probability of A or B is equal to, we add up the probability of A plus we add up the probability of B, and then we subtract that which is common to both A and B. And then, so that intersection there, that's the intersection symbol. Recall that the intersection symbol means and. Okay, so that means and there. And. The other one we saw was or. All right. So when you roll a number cube, the probability of even or prime is, well, the probability of even is 3/6. The probability of prime is 3/6, but you have to subtract off what's common to both. 1/6 equals, so you get 5/6. So again, what was common to both? 2. So 2 was common to both 2, 4, and 6, and 2, 3, and 5. We have to subtract off that 1. We have to subtract off 1. Otherwise, we'll be double counting. 1, 6. Okay, so let's see here. So find the probability on a number cube of rolling a 4, which is 1/6. You have a 1/6 probability of rolling a 4, Or an even number, it's 3, 6. So 2, 4, and 6. So you either have, a 6, or you have a even number 2, 4, and 6. And so notice here again that 6 is common to both. So the probability you roll a 4 is 1, 6. The probability you roll an even is 3, 6. But you should have to subtract off the event of rolling a 6, which is common to both. So minus 1, 6. So you get a 1/2. Actually, when you think about it right away, it becomes intuitive. 4 or even number, well, it's kind of like an even number trumps the 4. It doesn't really matter when you say 4 if you say even number. Anyway, so let's continue on here. There's that. Find the probability on a number cube of rolling an odd number, which is 1 through 5. Or a number greater than 2, so that would be 3, 4, 5, 6. So what's common? Okay, so we have a couple of them common, right? So 3 appears twice, and then 5 appears twice. So we have 2 outcomes which are common, so we're going to have to subtract off 2. So the probability you roll an odd is 3, 6, 1, 3, 5. The probability you roll a number greater than 2 is 4, 6, 3, 4, 5, 6. But then you have to subtract off the 2, which are common. Otherwise, you'd be double counting. And that would make sense. I mean, if you didn't subtract off 2, 3, 6 plus 4, 6 would be 7, 6. And that probability would be greater than 1. Well, that wouldn't make sense. Remember, probability goes from 0, including 0 to 1. Okay. Let's look at this example. A card is drawn from a deck of 52. Find the probability of each. You draw a king or a heart. So if you notice here, you have 4 kings, but then you have 13 hearts, but you've counted the king twice. So the probability of drawing a king is 4 out of 52. Of drawing a heart is 13 out of 52 and 1/4. And then, but you have to subtract off the king of hearts because it appears twice. So you have to subtract off 1 of 52. Now, why didn't they just leave it 4 of 52? Because, oh, I see, because 4 of 52 is, yeah, so 452 plus 1/4 minus 152. That would be 4/13. Probability of a king, you have 4 out of 52. The probability of a heart, you have 13 out of 52. Right, so 4 out of 52. Probability of a heart is 13 out of 52. But then you have to subtract off 1, which is common to both. So you get 4/13 is 17 minus 1 is 16 out of 52. And then when you divide by 4, you would get 4/13. 4/13. It's strange, why didn't he just write that 13 over 52? All right, let's look at the next one here. Now, with these here, I always suggest students make a table to kind of collect the information. So you'll get used to making a table with these, but I'll show you what I mean, and then you kind of fill in the table. Of 1,560 students surveyed, 840 were seniors. So there was a total. So this will always be the total column over here. So let me put that Well, let me put it there. So this will be my total column, and I'll highlight that. That's my total. Okay, of 1,560 students surveyed, 840 were seniors. Okay, there's seniors there. And then 630 read a daily paper. So paper readers here. So seniors, let me just say that. So seniors and then paper readers. Seniors and daily paper readers. All right. So there was a total of 840 seniors. And then 630, and again, I guess I can say this is total down here too. So this is total as well. When you make your table. So there were a total of 630 daily paper readers. The rest of the students were juniors. Okay, so how do we know how many juniors there were? Okay, so the rest of the students were juniors, so we kind of have to fill in the blanks here, right? So I have here, so if I take 1,560, which are total students, and I subtract the 840 seniors, then I know then I have 720 juniors. So we just start to complete the table. Okay, if I have a total of 1,560 and 630 were paper readers, then if I subtract 630 from 560, I get 930 non-paper readers. All right, so there was a total of 630 paper readers, and 215 of the paper readers were juniors, so that if I subtract 215 from 630, I will get 415 seniors read paper. And then again, we just fill in the blanks by subtracting. I have a total of 720 minus 215. That will give me 505 juniors who did not read the paper. And I have 840 seniors. 415 were paper readers, which means then if I subtract 415 from 840, I would get 425 seniors who were non-paper readers. So I always suggest you make your table, okay, with your totals, both here and there. All right, and then you just fill in what the blanks. So now, what's the probability that a student was a senior? So I can look at the table and answer that. I had 840 seniors out of 1,560, or read a daily paper readers. So there I have 630 out of 1,560. Okay, but this right here is what's common. So I used the 840 and I used the 630 paper readers, 840 seniors, but I see I double counted 415 twice. So I have to subtract off 415. So I get 1055 divided by 1,560, and that's 67.6%. Okay, let's look at another one. Of 160 beauty spa customers, so again, this is my total. So I have a total of 160. Okay. 96 had hairstyling. Okay, so I label my styling and then no styling. So 96 had hairstyling. And 61 had a manicure, so a total of 61 had a manicure. So I label manicure and no manicure, styling and no styling. There were 28 customers who only had a manicure. So there was 28 customers who only had a manicure. Okay. Oops. So let me put that in red. They didn't have styling. So 28 customers who only had a manicure. No styling included. Well, they gave me that, so let me put that there. I'll use the red for the ones I want to fill in the blank. So they gave me 28 had a manicure. Only, or 28 customers who only had a manicure. They didn't have styling. And so with that, then I can kind of fill in the rest here. So if there was a total of 61 that had a manicure, and 28 only had a manicure. Oh, there was 96 had a hair styling, and 61 had a manicure. And there were only 28 who had just a manicure. So then that means 61 minus 28, 33 also had a manicure and styling. And then if I had a total of 160 and 61 had a manicure, then 61 minus 1, or 160 minus 61, so that would be 99, had no manicure. And again, I can just fill in the rest here. So if I take 96 divided by, or subtract 33, I would get 63. Okay, so let me write. So that was 33. These are the ones that I'm filling in as I go along. And then 160 minus 96 gives me 64. And 99 minus 63 gives me 36. I should check 28 and 36 gives me 64, so everything checks out. All right, so now I can answer the questions. What is the probability that a customer had hairstyling? So there were 96 of those. Or a manicure, there were 61 of those in total. Okay, but I have to subtract off those who had a manicure and styling. Otherwise, that'd be double counting. So 96 out of 160 plus 61 out of 160 minus 33 out of 160. So that will be 124 divided by 160 is 77.5. Okay, now let's look at some applications here. So we have 6 students who are randomly going to choose a butterfly from a list of 8 types. So each of the 6 students can choose one of 8 types of butterflies. What's the probability that at least 2 students choose the same butterfly? Well, to get at that, the probability of at least 2 students is equal to 1 minus the probability that they all choose a different butterfly. So you have 8 butterflies. So the first student, okay, can choose one of the 8. Okay, so the first student can choose any of the 8. But then the second student has to choose a different butterfly, and they can do that in 7 ways. So they can choose any one, 7 out of 8. And then the third student has to choose a butterfly that is different than the other 2 students. Okay, so they have 6 ways they can do that. So 6 out of 8. And we go on down the line. All right. So the probability of at least 1. Now this represents here 876543. That represents a permutation, or 8p6. Okay. Eight items taken 6 at a time. And then the denominator is just 8 raised to the 6. All right, so when I evaluate that, 8p6 divided by 8 raised to the 6, that would be 20160 divided by 262144. So 1 minus 20160 divided by 262144, well, that would give me 241984 over 262144, or 92.3%. So there's a 92.3% probability that at least 2 students will choose the same butterfly. Okay. The interesting problem here is what's called the birthday problem, and this can be a lot of fun to actually do if you're at a gathering of a lot of folks and having a good time. In a classroom of 30 students, what's the probability that at least 2 have the same B-day, same birthday? So the probability that at least 2 have the same B-day is 1 minus the probability that none of them have the same B-day, or everybody has a different birthday. So 1 minus the probability that everyone has a different birthday, okay? Or none have the same B-day. Well, the probability that none have the same B-day, so you have 365 days, so the first person can choose one of 365 days, but the next person to have a different birthday now has 364 possibilities out of 365, and then we just go on down the line. Well, my numerator, 365, 364, 363, is just a permutation of 365 days taken 30 at a time, and then divided by my denominator, 365 raised to the 30th. So when you evaluate this here, you get 0.29368. Well, that's the probability that everybody has a different birthday when you have 30 students or 30 people. So the probability that at least 1 or at least 2 people have the same birthday, at least 2, is 1 minus the probability that nobody has the same birthday. And with 30 people, it's a pretty high probability, almost a 71% chance that somebody is going to have the same birthday. And doing this problem, I actually did it on decimals because these numbers get large. Okay, so I just did that on decimals. That was the probability that everybody has a different birthday. NPR 365 days, taken 30 at a time, and then 365 raised to the 30. So again, you'd find those statistics for choose NCR and NPR, and the functions and stats. Okay, pretty interesting problem. Okay, so that's it for mutually exclusive and inclusive. Mutually exclusive events that happen, that don't happen together, or can't. It's impossible for both events to happen at the same time, versus inclusive events where it's possible to happen at the same time. Okay, so mutually exclusive and inclusive events. So that's what we learned today.